So we're going to go ahead and start on page 34, go through constant acceleration. And I'm going to switch over to the iPad again so I can write on this as I go. So this time we're going to be filling in a little bit more information because with constant acceleration, we don't have everything is going to be zero. So let's start out. Our velocity is going to be changing. So it's no longer zero or a constant number. Now our accelerations are going to be a constant number. We don't know what it is. F net is going to be a number. And now we have unbalanced forces. So let's look at thinking about speeding up. So back when we did graphing, we had our graphs for accelerating items on position time graphs as being kind of flat near the beginning and then getting steeper and steeper as they went. And that could be either heading in the positive or in the negative direction. Our velocities would be a straight sloped line, and those would be heading away from zero for speeding up because the velocities are getting larger, at least as far as an absolute value is concerned. And then for slowing down, you start out with a speed and then it slowly goes to the point where it barely changes position. And for our velocities, they start out at some value and they head towards zero. Okay, so this summarizes all of what we've known about constant acceleration. Now let's do some examples on the free body diagrams. So I'm not going to ever have you have both horizontal motion and vertical motion at the same time. The math of that is a little bit too challenging for this class. So we're going to separate between when we have horizontal motion and when we have vertical motion, but we're going to go through the same steps as what we've been doing. So the first one has a 5 kilogram box. It's being pushed to the right, and it has a constant acceleration of 2 meters per second squared. It says a 20 Newton force is being applied to move it across the floor. Draw your free body diagram, label all of the forces, calculate all of the individual forces, net force in X and Y directions, and acceleration in X and Y directions. So let's go ahead and start labeling what we can. First thing is always that 5 kilograms inside the box. It's being pushed to the right, so that tells us there's an applied force. So FAPP to the right. They tell us that there's a constant acceleration of 2 meters per second squared. And since it's to the right, that would be an acceleration in the X direction. So that would be 2 meters per second squared, and you need to have some designation to the right. I'm just using an arrow to indicate that we're going to the right. You could write out the word right, but I think an arrow is adequate. The next thing we know is that what else do we have? We have the force of gravity. So we have the force of gravity going down. We're going to have a normal force because it's going to be being supported by the floor. It is going to probably have friction because it's moving across the floor. So we've got all of our forces written down, and then going back and reading in the problem statement, it says there's a 20 Newton force being applied to move it across the floor. So we can fill in our F applied as being 20 Newtons. What else do we know? Well, we know there's no motion in the Y direction, so we know the net force in the Y direction and the acceleration in the Y direction are zero. And that's everything we get from the problem statement. So while we can't fill out all 4 items in that box or that one area as being zero, we can fill 2 of them in as being zero. But be sure you keep straight your X direction as being your horizontal and your Y direction as being vertical. That is definitely a confusion that some students have. All right, so the first thing we can do, just like normal, we can start with our force of gravity. So our force of gravity is going to be the same as our weight, which is m times g. So our mass is 5 kilograms. So 5 kilograms times 10 meters per second squared is equal to 50 newtons. So we can fill in the force of gravity as being 50 newtons. We know that it's balanced in the vertical, so the normal is also 50 newtons. Now here is where we're going to deviate from the steps that we did in both at rest and using constant velocity. Since we have an acceleration in the x direction, we are going to have to actually apply Newton's second law of motion. F net equals mass times acceleration. And these all happen to be in the x direction. So our acceleration in the x direction was 2 meters per second squared. Our mass was 5, so we can fill those both in. 5 kilograms times 2 meters per second squared. Our acceleration is to the right, so we know that we're going to end up with something in the right. So 5 times 2 is 10, so it's 10 newtons. We know that the direction is going to be the same, so when we go back to fill it in our little chart, we're going to have 10 newtons, and it's to the right, just like our acceleration is. Okay, so this is where we may have run into problems when we were doing some of the earlier problems kind of in this section, that if we have a net force, have to have a net force of 10 to the right, we know that F applied has to be larger than our force of friction, and it has to be larger by 10. So that results in our force of friction being 10 newtons. So one way to write this down is saying that our F applied minus F friction has to equal 10. So if we've got 20 minus the force of friction equal to 10, we can rearrange and solve. We're going to end up finding that the force of friction is 10 newtons. All right. So vertical motion. A 3 kilogram bucket is being lifted using a rope. Well, we haven't had a rope before. To the top of a well. It's moving at a rate of 1.5 meters per second squared. Draw your free body diagram, label all your forces, calculate all of the forces, the net forces, acceleration, etc. Okay. Oh, since it's being lifted, we know it's going up. All right, so let's start with what we know. 3 kilograms, 3 in the box. And then we have gravity acting downwards. And then since it's being lifted with a rope, we know that it has a tension force. So we haven't used this in a while. So it's F sub TENS for tension. And we know it's accelerating at a rate of 1.5 meters per second squared. And this has to be in the Y direction, because this is the vertical direction and it's going to be upward. So we're going to want to draw an upwards arrow for that. We also know that it's got to be balanced in the x direction. So our acceleration in the x direction is 0. Our net force in the x direction is 0. We also know that our net force in the y direction is also got to be in the same direction as the acceleration. So we know that that direction is upwards. And that's everything just from the problem statement and knowing what we know about net forces and net accelerations. So we can start out again with our force of gravity. Force of gravity is equal to m times g, which is going to be 3 kilograms times 10 meters per second squared. So that is 3 times 10 is 30. So 30 newtons. So our force of gravity is 30 newtons. It is not balanced. So now we're going to have to go and figure out what our net force is using Newton's second law of motion. So our net force is going to be equal to m times a. Our mass is 3 kilograms. The acceleration is 1.5 meters per second squared. This is going to be 4.5 newtons. We already know that it's upwards. All right, so now we've got to figure out the force of tension. So force of tension minus the force of gravity is going to have to equal that 4.5 newtons. We know that the force of gravity is equal to 30 newtons. So from that, we can calculate that the force of tension is 34.5 newtons. Okay, so you are going to have some follow-up work here. You are going to have some additional work to do. Let me get us back on our PowerPoint. So you're going to work on pages blue 35 and 36. Take them one step at a time. Be sure to identify all the ones that are at rest or constant velocity because those have balanced forces and they're a little bit easier. And what you may want to do is just go through and do all the ones at rest first and all the ones at constant velocity first, and then go back and tackle the ones that have constant acceleration. But follow the steps. If you need additional paper to do this, go ahead. You don't have to feel like you have to cram it all onto this. And I will come back on the next video and go over all the answers. Good luck.